session 6 on the topic of neural and splatting. So we have 4 papers in this session, and we will have slight change in the order of the first and second paper presentation. So we will have the second paper first from online. The first presentation title is VR Splatting, foveated radiance field rendering via 3D Gaussian splatting and neural points. From Linus Frank, Laura Fink, and Mark Stemminger.
Hi, I'm Linus, and I will be presenting our paper VR Splatting, foveated radiance field rendering via 3D Gaussian splatting and neural points. This is joint work with Laura and Mark, and we are from the FAU Erlangen-Nuremberg in Germany. As the title might suggest, in this paper we combine 3D Gaussian splatting and neural point rendering in a foveated fashion for nice VR rendering. So, to start off, what is our problem that we want to solve? We want to have a pipeline where we capture the real world with RGB cameras. Then we want to process that into some kind of digital model. And then we want to render that interactively and in VR. This rendering in VR is solving the problem of no-view synthesis. The problem in general is stated as you're having a bunch of input images, for example here with the Opera House, and then you want to create novel views whereby you have fly-throughs or interactive rendering. The usual way to do that is to use differentiable rendering and have some kind of model, render that model, compare that to the ground truth image, and then update the model. So looking again at this overview, we look at the later 2 stages, because they are differential rendering, they are combined into one. So what's the problem? It's VR rendering. In general, VR has high performance demands which make the whole system a bit difficult. First of all, in VR we have 2 renderings. Second, we have very high resolutions. So here I've plotted the total pixels in a VR headset over the last few generations, and the trend is only going up and it's way beyond desktop configurations. And lastly, we have a high frame rate demand, as we need to hit our, in this case, 90 Hz frame rates. So looking again at this overview, we need to choose our model or our radiance field very carefully to allow for VR rendering. So what are some common radiance field representations? First of all, we can split that into essentially 2 directions, where we have implicit models, which are mostly MLPs or voxel grids, and we have explicit representations, which can be triangle grids or point clouds. For implicit models, the most well-known one is NERV, where you abstract the scene into a volume and abstract that volume into an MLP, and rendering is done via ray marching, where you have to step through the whole volume and accumulate your samples. That, of course, is a bit slow, so for VR rendering, that's not perfect. So we focus on explicit representations, and for us, that means point clouds. So in general, for differential point cloud rendering, the setup always looks the same. We have some kind of point cloud. It can, from, for example, structure for motion, multi-view stereo, or some active sensing like LiDAR. We have a bunch of cameras in the same coordinate frame as the point cloud. And when we render that point cloud from a camera, we get a rasterized version of that point cloud. We can compare that to ground truth, do that for for all our input views, and update the point cloud, so in the end we can render that point cloud from novel views. A common problem with point cloud rendering is how to fill the space in between all the point samples. And in a world before Gaussian splatting, the fastest way to do that was by a point sample rendering followed by a screen space filter, where you first optimize your point cloud and then you rasterize the points as small splats. And in the end, you use screen space filtering, which is commonly a unit to fill all the holes. For example, this paper of Ali and colleagues does exactly that. The point cloud is rendered, inputted into a unit, and then you have some result. It's compared to ground truth, and the filters of the unit get updated. But what is also possible in this setup is to associate each point with more than just RGB colors. So they here use a higher dimensional feature vector, which is also sometimes called descriptor, where you have, in this case, 8 floats, where you can store more appearance, which is then decoded by the neural network. That then might look something like this. To resolve occlusion information, they also use a multi-resolution rendering approach, where you render in progressively lower layers and feed that into the unit at the corresponding levels. This allows for very fine detail reconstruction. However, there's strong overdraw in lower layers, and there's temporal instability, which is not perfect for VR. This paper here, TRIPS, resolves that by basically making the splatting process smooth, so it's not point is not splatted to 1 pixel but to 8, and it's a trilinear splatting operation, so it gets smooth over the domain. This also allows the network to be much smaller, which accelerates rendering a lot. So is that ready for VR? Unfortunately not. Here on the right I have plotted the render times on the left with the amount of pixels demanded from the system, and we can see here that due to the screen space filtering scaling with the amount of pixels, we fall out of the VR limit quite easily. So how about the other direction, which is Gaussian splatting? There, of course, the setup is a bit different. We have our point cloud, we optimize the points, we split them, we make them larger, and in the end the whole image is filled once we rasterize. This, of course, is a nice explicit representation. However, to reconstruct fine details, we will need a lot of primitives. And that might also be a problem. Because if we don't have that, then fine details are missing. So here you can see in the bottom that the fine-grained details are basically missing, or you can see the individual Gaussian spikes there compared to the full 5 million primitives result. Why do I show that? That's because 3D Gaussian splatting scales with the amount of primitives. So if we look at here, we can see that the base configuration of 3D Gaussian splatting isn't able to be rendered in VR out of the box. And for example, we would need to reduce the primitives to the result shown on the right to hit the VR budget. So what can we do? A lot of things, but our answer to that was we want to use four-weighted rendering. For four-weighted rendering, the idea is that we exploit the non-uniformity of the human visual system to accelerate rendering. The human visual system is built that you have one fixation point, and then that what you fixate on you can see sharp and accurate, and stuff in the periphery isn't resolved at that high quality. That is due to the eye having two different kinds of receptors. One is the cones, which are centered around the fixation point, which is also called the fovea, and these receptors are responsible for resolving colorful and accurate vision. There's another kind of receptor, which is the rods, which are mainly distributed in the periphery. They are more focused on, or their task is more to resolve temporal information, for example. So if you have flickering in your periphery, the rods will be sensitive to that, so you want to avoid that if possible. For us rendering folks, it's basically you can just abstract the whole system into two parts. One is the foveal region, which is about 5 to 15% of the human visual field, and the rest is the periphery. There's of course a bunch of work in that domain. So, for example, you could do four-weighted rendering by using a multi-resolution rendering, where only the foveal region is rendered in full resolution, and you use quarter and half resolution renderings for the rest. However, here you need to have strong anti-aliasing techniques, again, to not have flickering. What's also possible is to avoid that by only reducing the shading rates and not the whole resolution to accelerate rendering. You could also go through the temporal domain, where you reproject previous frames to the periphery to avoid redrawing every frame every time. Or in the domain of radiance fields, you could use different models. So you have different radiance field for your foveal region and for your periphery region. And that's exactly what we also want to do. So looking again at these two graphs here, we can see that both methods, so Gaussian splatting and the neural point rendering with TRIPS, are not able to render in VR out of the box. However, we can see we can identify sweet spots here. So for example, TRIPS can render in low resolution very fast, and Gaussian splatting can render a coarse representation with a few parameters also very fast. And the added benefit here is that the Gaussian splatting representation is smooth, because the Gaussians are very smooth in general. So few aliasing artifacts will be there. So looking at that, we can see this Gaussian image here is not as high quality as we would want. The TRIPS rendering compared to that can do that, and if we combine them, then we have the best of both worlds, hopefully. So this is exactly what we do. We have a three-step approach where we first render a coarse Gaussian splatting rendering for the periphery, then we render a detailed neural points rendering for the fovea, and we combine them together. So looking at our pipeline, again, first we render the Gaussian splats. Here we need to note that we will have to use some kind of popping-free version. So in this case here, we use stop the pop because these small popping artifacts, which are basically sorting inaccuracies, they can be quite visible in the periphery. For the fovea neural point rendering, we now query the eye track at this stage, because we will have basically deferred the update as long as we could to get the most accurate eye tracking information, and then we use that for culling. So we use a two-step culling approach, where first we use a frustum culling, where basically we throw away all points outside of this foveal subfrustum, and secondly we use a inclusion culling, where we output an approximate depth buffer from the Gaussian splatting representation, which we can use to throw away points too far away. With that, we have then a small rendered crop for our fovea, and we feed that into our small neural network. Here, again, we also input the color from the Gaussian splats. So we use we use the multi-resolution point renderings, which we get, and secondly, we use the coarse Gaussian rendering and let the network combine that. That has the added benefit that the neural points really only need to encode fine detail, and we can rely on the coarse Gaussian rendering to get a general appearance. Then we have two images. We combine them with a blending function. We here use an edge-aware blending function. For details, you can look in the paper. The results look as expected. So wherever the user is looking, there's fine details added, and we have a coarse general representation in the periphery. We did a user study versus base Gaussian splatting to evaluate our method further. So we asked 12 participants in 240 trials and 76 preferred hours in a 2 alternative force choice setup. For evaluation, this showed the two methods that we compared in the user study. So once our method and then a VR-ready 3D Gaussian splatting version, which has lower amount of primitives, and we are in the same ballpark, so we are able to reach to stay below the 11 milliseconds threshold. Compared to other methods in that field, for VR radiance field rendering, we outshine them by quite a bit. For details, you can also look in the paper. What I want to also mention again is temporal stability and popping, because in the beginning of the project, we first did a small study, and the result of that was that popping is very distracting in VR. So using some kind of sorting, some kind of way where the Gaussians are sorted correctly is very important. As I said before, we use stop the pop here. However, their rendering adds about 2.3 milliseconds to our system. So what we need to do is we need to reduce our primitives even further. And we did that with a gradient opacity penalty for all points. So we basically pushed the gradients of all primitives a bit towards transparent, so that they could be removed. That's a very nice way to reduce primitives without affecting quality too much. To look at some limitations and further work, First big limitation of our system is our reliance on the eye tracking accuracy. In our tests, that wasn't always there. So we essentially had to increase the size of the fovea a bit to cope with that. So small inaccuracies in the eye tracker otherwise might be visible, and if we basically make the foveal region, which we render a bit larger, we can avoid that. So there's probably more performance gains there with better eye tracking. Furthermore, we inherit limitations from the approaches we build on. So for TRIPS, for example, there's no densification or point cloud augmentation. And for Gaussian splatting, there are floaters and there are perspective artifacts. The latter can be solved with a bunch of new approaches. For the former, there's always a bit of an issue, especially because we use very few amount of primitives. It gets a bit more floaty, the system. And lastly, an interesting direction for future work is that probably with other densification strategies, you could reduce the number of Gaussians even more. So as you saw in the examples that I showed, the peripheral rendering still looks quite okay, and you could probably reduce the quality and also the times used rendering there even more. However, you would need to adjust the densification strategy a bit to allow for that. As an example, we tried the now popular MCMC strategy, and what we noted there is that while with the same amount of primitives we got better results in the central objects, the background degraded too much and it got a bit spiky, and that is again visible in VR. So to conclude, we present a system where we combine 3D Gaussian splatting and neural point rendering. We use 3D Gaussian splatting for the peripheral rendering because we can use the smoothness of the Gaussians in a low primitive setup. And we use the benefit of neural point rendering for fine detail. And as that scales with the amount of pixels that we require, that's basically a perfect match between these two methods. So with that, thank you for your attention. And I'll be interested for questions. And you can also send me an email if you have questions.
Okay. Any questions from audience?
So, okay, thank you.
Yes, hi.
Right. So thank you very much for your work. I think it's very interesting. But I see that, of course, that you used the neural point rendering for the foveated part. And as we all know that there are some problem in terms of if the it's a learned renderer, right? So if it deviates too much from the training views, there will be some problem. So and your further focus is on VR. So there will be a situation where the user want to go very close to the surface or very far away, I don't know. So have you encountered any kind of this kind of problem where the learned renderer has not, need to render outside of the learned space? Do you have this kind of serious situation?
So not really. It wasn't that bad, to be honest. So the renderer or the neural components in that renderer is very small. So it's more or less decoding and hole filling in image space. If you get too close, there is some shine through. But to be honest, it's kind of similar to Gaussian artifacts, which get a bit spiky if you get very close. So it wasn't so bad for us.
Right, because the RGB output from the 3D.js has stabilized essentially. That's,
yes. Yes.
In
a pure neural point rendering, that's worse. But because we input the Gaussian coarse rendering as well, it's not that bad.
Yeah, understandable. Yeah, that should be the case. But still, I'm curious how if I get very close to the surface, because when VR, right, you may want to you don't know what the user will do and try to look at the scene. They may want to go very close to the surface. So I don't know. Maybe I can write an email to you later to ask for some result. Anyway, another question I have is that I'm sure that you have also know about the there's a foveated rendering work for NERV, in which that for the outer area, they use a much smaller network to make it much faster. So have you considered a similar methodology? So of course that I'm sure that 3D.js can already handle cost in your case and in your context, or can handle cost rendering. But have you also considered using, perhaps what you can also consider do is to use a weaker network for the surrounding area? Have you considered that direction as well?
Yes, we did. Originally, we thought about just using neural point rendering and using a small network in the periphery. The issue with that was a bit too much aliasing there. Right. So I think the screen space filter there caused a bit of aliasing, which was noticeable. Right. So for the foveal region, it's not noticeable, but in the periphery, if you like turn down the strength of the network, then it gets a bit worse.
Okay, yeah, because I think that the but perhaps you already answered my question, because I imagine that another architecture is that you can use a very coarse 3DGS, so very sparse 3DGS, and for the outer region you use a weaker network, and in the center you use a stronger network. But perhaps you already told me that there's a stability issue with that kind of architecture. Yes,
I mean there's a small issue with densification for like very sparse and coarse 3GS. That's what I meant with the limitations part. I think you need to adjust your densification strategies a bit to allow for that.
Okay, so I guess I don't know, too much time. Okay. So I guess my last question is that you know that 3DGS, of course, if the particular area you take a lot of pictures, is much more stable. But and I see that you're using the output of 3DGS to stabilize the renderer. So what will happen if there are areas where the 3DGS is not given a lot of training samples, and what kind of like situation we'll see over there?
It will be similar to the neural point rendering. So if you don't have enough like training samples from like areas which are only observed in one view, that's the only appearance that you get there. So it will deteriorate a bit. The quality will be worse there.
Yeah, but the kind of is normal. Yeah. Okay. Thank you very much. Thank you very much, sir. Okay.
Any other questions from audience? All right, then thanks to presenter.
Thank you.
Our next paper is LS-NIF, locally subdivided neural intersection function, authored by Shin Fujieda, Ji-Chen Kao, and Takahiro Harada. So Shin will present.
All right, thanks for the introduction. So I'm Shin Fujieda from MD, Advanced Rendering Research Group. Today, I'm happy to be here to share our research, LS-NIF, locally subdivided neural intersection function. Actually, there are other papers in this section for the splatting, but this work is not for splatting. This is like replacing the bottom level BVH traversal using neural geometric representation to accelerate the late query operation. So let's get started. So in the conventional ray tracing pipeline, late query is the important operation to find the ray geometry intersection and extract some geometric properties like normal and depth and something like that. And late query is usually accelerated using BVH, and typically using this kind of two-level BVH as shown here. Sorry. However, this BVH traversal exhibits some irregular execution pattern, such as branch divergence and unpredictable memory access to traverse this tree-like architecture. So it's difficult to achieve some like a maximum efficiency on GPU. Dedicated hardware accelerated somehow, but it cannot fully mitigate expensive workload. Then instead, there were some researchers using neural network to accelerate some kind of late query operations, but they still have some major restrictions. First, neural intersection function called NIF is our previous research integrating neural representation into the conventional path tracing pipeline. Given an intersection point between a ray and the ABB of the object, then the neural network determines if the ray is occluded or not without traversing the bottom level BVH. It allows for fast shadow ray query, like to report if the shadow rays are occluded or not. However, NIF requires online training of these neural models depending on the current viewpoint and the lighting. So it cannot deal with some like dynamic contents like a moving camera and changing light condition, and and so on. Also, while it can be applied to to query other geometric properties such as normal and depth, the visual artifact is slightly too large to be practical. So NIF only supports a shadow lay query in the practical solution. And also another research, NVVH, which eliminates the requirement of online training and support any types of lay queries in the neural lay query pipeline. And to reconstruct high-quality signals, it ensures that the encoded point is closer enough to the surfaces in using the intermediate VVH node. Although NVVH doesn't require any online training, by learning arbitrary lays in the entire scene, the model need to be trained on per scene basis. So we need to train the different neural models for different scene settings. This restriction prevents further modifications such as object transformation and some like an interaction, like adding object into the scene. To overcome these challenges, we propose to extend NIF, which we call locally subdivided neural intersection function, called LSNIF. LSNIF can pre-train the neural models for each object, not for the entire scene. So we don't need to train the model during rendering, and we can use the same trained model for the instanced object. We can reuse the same trained model. And LSNIF supports some scene changes such as camera movement and changing lighting conditions and object rigid transformation. Rigid transformation. And LSNIF also supports all types of lays. However, we restrict its usage to non-primary lays in this work because errors introduced for primary lays is kind of a bit too large to be practical. And in the conventional path tracing pipeline, after finding the intersection with the ABB of the object, we traverse the bottom level VVHs. But on the other hand, in our proposed hybrid path tracing pipeline, LSNIF can be used for some complex geometries instead of traversing their bottom level VVHs. So using neural network to infer some geometric information. And the LSNIF representation is much more compact comparing to the standard VVH. So I will show some good quality result and performance later. Okay, this is an overview of our method, LSNIF. I will explain each step later, but here, let's first consider the challenge we have to resolve. We use a small MLP together with a fixed size grid, then to allow the small MLP to easily infer the desired shading information like occlusion, normal, and something like that. We need to ensure that each input feature to the MLP should uniquely represent a specific lay. So here, let's consider the lays with the same direction, but originating from different points, as shown this orange and blue and white here. And in the previous NIF, the input to the neural network is constructed with outputs from two different 2D grids. One is for intersection position on the ABB, and the other is for the lay direction. And considering these three different rays, orange and blue and white here, they are actually different, but they share the same direction. So the output from the direction feature grid, this blue grid, are same for these 3 rays. So which makes it difficult for MLP to distinguish these features. And if the viewpoint is fixed, variation of the output signals that MLP need to reconstruct is kind of limited. So this approach is still effective. However, this leads to another drawback of not supporting any dynamic content, like a viewpoint change, which requires the retraining of the model. And one straightforward solution is to use the 4D grid to encode each pair of position and direction at the same time. Then we can distinguish all these lays properly, but it's computationally very expensive and very memory intensive, so making it impractical for real-time applications. Another solution to improve the reconstruction accuracy is to use more data as input to the MLP. So LSNF uses this strategy by boxerizing the AABB into a low-resolution grid. Then the intersection point between a ray and these box cells are used as an input to the MLP. And this approach makes more variation in the input, allowing the MLP to more efficiently distinguish between input with different features. And as a result, LSNF can more accurately reconstruct the original geometry. Okay, now then let's get back to each step in this LSNF. Again, LSNF are optimized for each complex object, not for the entire scene. So, and it generates the shading information instead of traversing the bottom level BPH. Then first, we compute the intersection point of a ray with the ABB. Then using a classical DDA algorithm based on these two intersection points, then we calculate the hit point of the ray to the surface of box cells. Here, we only consider the box cells containing any object triangle, like shown white here in this figure, while ignoring the empty box cells. Then we encode this hit point with a multi-resolution sparse hash grid, where feature vectors are located only on the box cell boundary. But anyways, I will explain this specialized grid encoder later. But thanks to this voxelization methodology, different rays can be encoded into different features only using a single 3D grid. And we concatenate this feature vector from each hit point and feed it to the MLP as an input, then to predict the geometric properties for the ray. And in this LSNF pipeline, two important building blocks are voxelization and multi-resolution sparse hash grid encoding. Firstly, voxelization effectively distinguishes the different rays that have different characteristics. That is, meaning that each input feature should have unique representation for a ray. Also, it doesn't require any explicit occupancy checks, like compared to the regular interval sampling as NAF does. So what we need to keep here is just binary occupancy information for each box cell. And we introduced multi-resolution sparse hash grid encoding for our box cell representation. And with LSNF, all these hit positions are always lying on the box cell boundaries like this. So no need to consider the position inside each box cell. So meaning that we just need to encode the position, position on the boundary. So let's focus on the area around this yellow square. I hope you can see this yellow square, but yeah. Let's focus on this area. And in a sparse grid encoding, feature vectors are only stored on this box cell boundaries shown in this grayish points. And other features are just ignored. So we only need to store some features on the box cell boundary. Then, since all the features are located on the boundaries, it reduces, of course, the memory footprint comparing to the standard grid. And it also reduces the number of queries to the grid features, which improves the performance too. For example, in this 2D case, standard grid needs to query 4 times for bilinear interpolation to achieve the final feature on the target point, the red shown here. On the other hand, in a sparse grid, we only need to query 2 times, since the target position only lying on the box cell boundary, requiring only the linear interpolation to get the final feature on the target position. So, until now, we've studied how LSNF works for each object. Then, now let's consider how we integrate this LSNF into path tracing pipeline. And LSNF is designed to support all types of rays, but yeah, as I said, if using it for primary rays, the visual errors are too large to be practical. So in this work, we restrict its application to non-primary rays. Instead, for primary rays, we use rasterization to create G buffers storing like shape and phase indexes and UV coordinate and camera distances, as shown here. And this approach requires to store the vertex and phase information, but eliminates the need for the BPH construction for the object replaced with LSNF. And we use LSNF only for the complex geometries, not for the scene. So for non-primary lays, we first traverse the standard two-level BVHs for simple objects, in this case, the corner box here, to find the intersection to them. And this BVH should be very shallow and small. Then to find the intersection against LSNF objects, like a complex object here, like a bunny and dragon Thai statue here. And we construct a dedicated top-level BVH for the ABBs of these LSNF objects and traverse it in runtime. The simplest implementation here is to execute LSNF in the BVH traversal, but it introduces some data and code diversions. So instead, here we first collect all the hit points, all the hits between the lay and the LSNF object by traversing the dedicated top-level BVH, and then execute LSNF, like by running DDA, applying sparse hash grid encoding, and executing neural network inferences as a batch process for these all the hits. Then finally, we combine the lay's hit information for these two phases and achieve the final sharing results. This pipeline may not be the most optimal in terms of computational complexity, but it should be well aligned with the modern GPU architecture and programming model. This compares the memory footprint of LSNF and the standard BVH. Again, to use rasterization, we need to retain vertex and face information for all the geometry. But additionally, for simple object, we store the data of BVH nodes for the corner box here. And on the other hand, for complex geometry, we store the LSNF model instead of BVH nodes. So in this case, bunny here. Then which achieves up to 106 times reduction in our experiments in memory size. And this vertex and face information for complex geometry is not required if we can use the LSNF for the primary lay too. That leads to further memory reduction, but it's kind of our future work. So okay, for now, I explained our techniques. Then let's see some results with our LSNF pipeline. First, I'll show you the quality evaluation against free pass trace results. So this is the first scene from the Blender's Machine's classroom. The removing LSNF object, the scene is rendered like this. And adding the LSNF object, then we can render like this. So this is without LSNF object, and this renders using standard BVH, and this is adding the LSNF object. And so these desks and chairs are instanced object. So in this chain, there are 50 LSNF objects in total, but we need to train just 15 LSNF models here because our model is optimized for each object, and we can use the same trained model for instanced objects. And this is one of the benefits of LSNF, optimized for each geometry, not for the entire scene. And this is rendered result with path tracing, and I get back and forth. And this one is LSNF, and this is path tracing, and this is LSNF, and this is path tracing. So this shows a flip error. So we believe the difference is not too large. And if I think we show only the rendered image with LSNF, it should be kind of difficult to decide if it's path trace or rendered with LSNF. And this is another challenging scene with highly detailed geometries. And without LSNF object, the scene looks like this. And adding LSNF object, then like this. So these trees are rendered with LSNF. And this is the path trace reference results. So this one is LSNF, and this one is path tracing. And again, LSNF, path tracing. So, and this shows the flip errors. Actually, we can see some difference between them on this scene, but we believe this is still visually plausible. Then now let's break down the memory footprint of the LSNF model. A single LSNF model occupies only 1.56 megabytes, where 4 kilobyte for voxels with binary occupancy information, and 62 kilobyte for the tiny MLP, and about 1.5 megabyte for sparse grid encoder parameters. And to evaluate the memory footprint of LSNIF, we compare it with the compressed BVH with a BVA compression method which Irritator proposed. Then this compressed BVH is an 8-wide BVH, and each internal node takes 80 bytes. And this table shows memory footprint of performance comparison for several machines. So the important things I want to mention here are two things. One is LSNIF reduces memory footprint up to 106 times comparing to the compressed BVH. And this LSNIF column shows memory footprint of LSNIF, and this column shows the compressed BVH. So we can achieve up to 106 times reduction. And the other thing is LSNIF can achieve better performance for multiple machines, comparing to path tracing efficiently for, especially for complex machines and machines with many instance objects. So yeah, if we want to know more detailed comparison, please check out our paper later. And LSNIF supports limited scene changes such as camera positions, object transformation, and writing conditions. So yeah, now let's check it out. So this is, so first, this shows the camera position changes. We can move viewpoint interactively with LSNIF object. So these 3 dragons are rendered with LSNIF. And then this changes the object transforms. So you can move, scale, and rotate LSNIF object interactively like this. And as you see, reflections and shadows correctly follow these changes. And also you can change the lighting condition like this. So this shows the example of point light. But of course, the LSNIF supports any types of light, like area light and environment light, and so on. Yeah. Then finally, I'll comment some limitations of future work of our research. We use rasterization in our hybrid rendering pipeline to render the shading information on primary layers. However, this requires us to retain vertex and face information of all the geometry, so which occupies some geometry memory footprint, of course. So if we can apply LSNIF for primary layer 2, then we can also omit them from the memory. So achieving higher quality result for the reconstructed geometry is one of our main future work. And as shown in the video, LSNIF only supports limited scene changes and doesn't support deformation without additional training for now. And also, LSNIF doesn't predict texture coordinates for now because errors in texture coordinates directly result in visible artifacts on the textured objects. So finding the stable training method for these deformation and error-sensitive texture coordinates remain challenging and should be focused for our future work. And last but not least, we only apply LSNIF for geometries without LODs in this work. So storing multiple LSNIF models with different voxel sizes for different LOD is a kind of simple solution, but inefficient in terms of memory usage. So further analysis is required to develop a more efficient LOD representation for LSNIF. So yeah, finally this slide summarizing our method to LSNIF. But so as shown here, we can show some more result with different scenes. So please check it out our paper later. Yeah, that's all. Thank you.
Thank you, Shin. Any questions?
Hello, cool stuff. Thank you for the talk. I have a question about how the logic works when you hit LSNIF surfaces when you're traversing down the BVH. It sounded like you store them and then later execute them. Like you kind of like defer the execution of evaluating the ML logic until after. Does this mean that you have to like store one entry per pixel of every possible ray that might have hit a surface and then compute or do an indirect dispatch later and reevaluate it all? And does that mean how do you handle closest hit scenarios like for opaque geometry? Or like what if there's actually something behind that you would have to trace again, right? Maybe I'm misunderstanding something.
sorry, what question? Okay.
So basically, we have two implementations. So mostly the implementation we use for this paper is like everything is written in HIP. So ray tracing is written in HIP, and also inference is also written in HIP. And then we can do like whatever we want to do. So we are like splitting the execution of the inference. So on the head of this LSNIF object, we are going to like just store the information so that we can defer the execution. Yeah. So yeah, this way we can use this WMML or matrix core on the GPU. So that's how we implemented. But we also implemented like a DXR. So in there, the execution is very bad, to be honest. But like, yeah, it's just a proof of concept in the cross-test hit, or yeah, in the hit shader, or we just run the inference. So right. That's right.
Yeah.
That's right.
All right. Any other questions from audience?
So you said one of the rationale for this was to reduce or to improve coherence of rays. Did you measure that, or why do you know why you're getting twice the performance? Is it just you have less memory?
So actually, this neural network inference is kind of like a fundamentally the multiple matrix multiplication.
Right.
So they're comparing to the like a B-based traversal. So it actually shows some like a branch divergence, code divergence. So instead of that, we can use like a how to say the maximum efficiency of GPU, and give me the performance number, this one. So
I was just wondering if you had some rationale behind these, or if it's just measured performance. Is the improved performance due to, well, we have less memory, so there's less bandwidth, or is it here execution is more coherent?
Actually, so I haven't measured the like that kind of detail measurement, but so we can get a better performance for the like a complex machine than many instance object machine. So if the machine contains many instance objects, so we can use the same model for the instance objects. So that's why probably we can just like learn the inference for one model to get some like sharing information for this object. So maybe that's why made it faster.
Thanks. Okay, this is a bit of an open question, but did you also consider just taking the scene, simplifying it, like back into triangles, but just less triangles, and then creating BVH over that and using that for secondary arrays? Because that's also much smaller. Just having less triangles means smaller BVH. So here you're suggesting simplifying the scene in the end with a neural representation. Did you also consider simply just simplifying the scene, building a BVH over that, and using that for secondary arrays?
Good question, actually. So actually making the like how to say it. So honestly, we are not measuring any performance like preparing the like other BVH construction, make it simpler and So honestly not sure. So maybe in the future we need to measure the performance against that. So maybe the other kind of like BVH to prepare some like node containing the more like how to say it? More sorry.
So first is like a self-intersection. So you are switching the geometry from like a fine geometry to coarse geometry. So you are going to find like a lot of issues there. So you may find a lot of shadows and things like that. And also there are a bunch of like meshes you can't really decimate. For example, the hairball, if you want to reduce it, it's just like it doesn't work. So that's another like problem. But like we are kind of like doing fairly well to hide it. So that's how I would say. But yeah, self-intersection can happen here, but it's not that like noticeable. So yeah.
You still have
I just still have a question related to the question about like ray coherence. I'm just thinking about the implementation of the kind of deferred execution of the evaluation and wondering if you're also doing any kind of like binning to restore. Because like if you were previously tracing all these rays together, there might have been some spatial coherence of, especially for like directional shadows. And you'd lose that if you defer all the execution until later, unless you repack them in a specific way. Have you thought about doing anything like that, or do you currently?
Could you repeat that? Okay.
So
sorry.
Because you're like deferring all of the execution of the neural network based BLASs, they all get kind of like atomically bump allocated into some buffer. So like kind of swizzled, like they lose all their locality and coherence. Do you do any kind of binning to restore that as to what you would have had if you had traced them in line in the screen space?
Sorry. So yeah,
We do sort.
You do sort.
Yeah.
Okay, hopefully you can talk with authors after this session. Okay, the next paper is I3D, efficient and selectively controllable text-driven 3D content generation with Gaussian splatting by Huichi Wu, Li Yao, Jianbo Mei, Yinji Wang, and Yinling Wu, Chu, Jingxia Yu, and Ilong Liu. So presented by Huichi.
Thanks a lot. Good afternoon, everyone. This is my first time to stand on the stage to introduce my paper, so I may be a little bit nervous. Okay, let's start introduce my paper. It's about test-driven 3D content generation with Gaussian splatting. We propose a novel controllable text-to-3D content generation method with multimodal self-optimization, which can refine the input text into richer prompt and optional integrate additional conditions such as style, canny, scribble, and pose to enable the generation of controllable 3D result. We also combine multi-view information such as multi-view depth, mask, features, or image as constraint to ensure multi-view consistency and enrich the details of other views. Our approach can effectively balance generation time and quality, offering new potential for the practical application of 3D content generation. Initially, based on the user's simple input text and additional condition, we use GPT-4 Vision to generate a preliminary set of prompts. These prompts are then used to generate corresponding images. The generated images are evaluated across multiple dimensions, considering factors such as the number of objects, their attributes, entities, relationship, appearance, and overall similarity to the user's original input. Each image is assigned a quality score ranging from 0 to 10. Subsequently, GPT-4 Vision analyzes the discrepancy between the generated image and the user's original input, providing insight into the errors and suggestions for adjusting the text-to-image prompt to improve image quality. Through multiple interactions, the image achieving the highest visual quality score as assessed by GPT is ultimately selected as the foundational image for subsequent 3D content generation. Score distillation sampling proposed by Dream Fusion can optimize the 3D Gaussians by measuring the difference between the Gaussian noise added to the rendered image and the predict noise, providing a direction for updating the parameters. We integrate the multi-view diffusion model into our pipeline, use XDS based on 4 generated views. Specifically, in each interaction, 4 orthogonal views are rendered from a 3D Gaussian. These views are then encoded into latent representations and pass through the multi-view diffusion model to calculate the diffusion loss in image space. The computed loss is backpropagated to optimize the parameter of 3D Gaussian model. We observed that even with multi-view SDS training interaction, the generated Gaussian function often appear geometrical, blurry, and lack details. This can be explained by the blurriness of the SDS loss. This observation led us to design the following for the multi-view information constraint. The first stage preliminary focus on constrain the geometry structure of the generated content. The second stage is dedicated to optimizing the appearance of the generated content. Initially, a multi-view diffusion model is employed to generate image from multiple viewpoints. Subsequently, a monocular depth estimation model is used to predict the depth maps of these views. We also employ a scale invariant loss function that accounts for both the monocular depth scale and the 3D Gaussian depth render scale. To ensure depth prediction across different scales, a multi-scale loss is introduced by interpolating both the predict and the ground truth depth maps at various resolutions. Different scaling factors are applied to the predicted and the ground truth depth maps. The depth loss is computed at each scale. In addition, we also add mask loss to further impose geometry constraints. The image masks are extracted from the alpha channels of these images. The loss is subsequently calculated by comparing these masks with the transparency obtained through Gaussian rendering. Our goal is to establish a visual feature correspondence between the reference view and the render view. This is achieved by enforcing feature-level similarity, guiding 3D Gaussian to effectively fill the gaps in visual regions. We utilize the Dino feature which are more robust to appearance variations and construct our loss function based on the cosine similarity between the Dino features of the input and the render image. Since Dino features are defined at the image patch level rather than at the pixel level, they enable optimization of high-level semantic consistency in the images. By incorporating feature loss, we can ensure that the generated image is closer to the reference image in terms of semantic content, which is essential for producing more natural and consistent content. With the initialization texture in hand, we first render a blur image from an arbitrary camera view. Next, we introduce render noise into the image and apply a multi-step denoising process. Use a 2D diffusion prior to obtain a refined image. The refined image is then used to optimize the texture while a mean square error loss. We also adopt a method that symmetrically updates the specific 4 viewpoint to optimize the texture. We compute the loss between the render image from the 4 specific viewpoints and the corresponding image generated by multi-view diffusion model. This is some results of our methods. Our method can generate 3D content in a short amount of time with a time cost similar to Dream Gaussian. Is able to generate more complex and richer 3D content compared to Shape E and Dream Gaussian. Among these test to 3D models, our approach takes the less time to generate 3D content while maintaining viewpoint consistency. In Table 1, we evaluate our method using clip similarity. We report the clip similarity and average generation time for different test to 3D models, calculating the similarity between the image generated by each model and the corresponding test. Our model perform well in terms of both generation quality and speed. We further compare our model with other image 3D approach. Our method require less time for generation while ensure multi-view consistency. Additionally, in example of a pair of 10 cowboy boots, both 0123 and Magic 123 fail to generate a complete pair of boots, producing only a single boot instead. In contrast, our method successfully generates a full pair of boots. Our method can generate more reasonable and consistent content in a short time. This figure shows the comparison between our prompt optimization results and our work result. Previous work often produced prompt that, when used for image generation, fail to generate complete object structure, making the result image unsuitable as a foundation for 3D generation. Since our focus on optimizing prompts for high-quality 3D content generation, our model places greater emphasis on aspects such as the style, geometry, texture, and pose of the object, while also highlighting elements such as the soft lighting, soft color, and 3D render. Our prompt optimization model is better suited for generating 3D content. In addition, we compare the performance with the latest work MV control in terms of controllable generation. The first figure shows that when we input the same text and scribble condition, our method takes 10 times faster than MV control, and the generated content is more complete. In addition, the details such as hands and feet are handled more accurate. The second picture shows that when we input the same text and the caddy condition, the visual effect of our model's multi-view prediction is significantly better than MV control. We also demonstrate the capability of our method in artist creation. Our framework can extract the content of images such as color, shape, style of hat, and perform artist creation, generating more wonderful content. In addition, our framework can effectively understand the content of images such as the characters, appearance, physical features, and can also produce coherent and high-quality 3D content. This is some application results. The first row shows results without multi-scale depth, while the second row demonstrates the result of multi-scale depth. As observed, incorporating multi-scale depth significantly improve overall depth estimation performance. The second picture illustrates results of multi-view information. The first row shows the render result with multi-view information. It can be observed that without the multi-view information constraint, the rendering results from perspective other than the frontal view are significantly worse and lacking detail. As we all know, it's difficult to generate high-quality results with simple text alone. However, by using a multimodal interaction self-optimization framework, the efficiency of generating high-quality content can be significantly improved. Since our model can extract mesh from 3D Gaussians, this mesh can be applied to downstream tasks such as animation. The figures below shows some of our results with rigid animation. That's all. Thanks for your attention.
Okay, thank you. And any questions from audience?
Yeah, so I'm just, I might miss some of the details, but I just want to ask, since you compared with the Dream Gaussians, Is there any specific reason for your model is like outperformance compared with stream Gaussian in like runtime or some other parameters here? And my second question is like, since you mentioned there is a the comparison of the not just from the text to 3D, I think it's the next slide. Yeah. So I think you also compared with the from image to 3D model methods, right? So those methods, like how many input are they taking? Like one or bunch of the 10 or something like that?
Okay, thank you for your question. We compare to Dream Gaussian because Dream Gaussian is input is text or a single image. Useful information is truly told to generate wonderful results. And in our method, we use four multi-view diffusion model to generate 4 viewpoints symmetrically to constrain the result, so we can get better result. And to compare to Gaussian Dreamer, it takes more time because it uses both 3D diffusion model and 2D diffusion model. It uses 3D diffusion model to generate point cloud to initialize 3D Gaussian. So this process takes more time. So our method takes less time than Gaussian Dreamer.
Yeah, that's the answer I'm looking for. And also the other additional question is, since you mentioned you compared with some other like directly from image to 3D, are those methods, because it's like a little bit small to me, the text, so I'm not sure, are those methods like only take one single image?
Yes, 0, 1, 2, 3, and image 1, 2, 3, they just take one single image.
Okay, that's interesting. That's fine.
Thanks.
Okay, so thank you for your contribution. I'm just wondering, how would you describe your work in relation to Coin3D, which is a work that is also about 3D content generation. SIGGRAPH 24, they uses a bunch of proxy shape as a guidance for 3D content generation. So are you familiar with it?
I use guidance condition, right?
Sorry? Coin3D from SIGGRAPH 24.
Const3D SIGGRAPH 24.
Yeah, there's a paper that, anyway, doesn't matter. Perhaps we can talk about it offline or anyway. They use it, so what they have proposed is that you can use a bunch of 3D shapes. For example, you want to make an apple. You make a shape in Blender that is a rough shape of an apple. And then this 3D proxy object can be fed to their model as a guidance for generation. So because so therefore, I would like you to have your comment on how your work is related to theirs and what how would you perhaps differentiate them? Yeah.
Yes, in our framework, we use AI tool to help us to generate 3D content. I think we can get this better result is contribute to GPT-4 vision. It can not only input text but also can input condition images such as canny, scribble, this shape to GPT-4 vision, and GPT-4 vision can learn the shape of this content.
Okay, thank you.
Yeah.
Perhaps we can also talk a little bit more offline.
Yes, we can communicate later.
Okay, thank you. That's all.
Okay, thanks. Any further questions?
Sorry to ask again because I want to continue my second question. Yeah. Can you go to the image to 3D that result slides?
This one.
Yeah, yeah. So my eyesight maybe not that good, so I cannot read this. Sorry. So is this saying that your performance is like all performance compared with all those methods here?
Yeah.
But if this is only a single image as an input, so there are some other like existing SOTA single image input like trailers, or it should be called trailers, or like some other like could allow like around 10. It's just 1 to 10 is not big difference. So there are some 10 images as an input, like Duster or some like faster or something like that. Duster 3R, Master 3R, those could kind of matter. It only take like a little bit few more images as an input, but the output performance could be boosted up. So have you ever considered like, is it necessary to compare with those methods, or you think it's totally different story? So my question is, this is the comparison with a single image as an input, and you beat them. There is some existing SOTA method, maybe trailers, which is only take one image.
Because in our model, we just in first we just generate one single image, and in later we use multi-view diffusion model to generate multi-view image. But in the start, we also use a single image, so we compare to these single image models.
Yes. The reason I mentioned, that's a good reason actually, but the reason I mentioned trailers is because I see the times is like minutes, 10 minutes, 15 minutes, 18 minutes, but trailers is like much more faster. Just after one click, you could, that's a pre-trained model, so it's very easy to faster. So that could be more challenger if we add that into the comparison into system.
Yes. So, in our model, we use Gaussian splatting for 3D content generation, but in image 1, 2, 3, it uses neural render field. It takes more time to generate.
Okay. Thank you. I understand this. Thank you.
Okay, let's thank to the presenter. We have last paper, split map online dense molecular SLAM with a 3D Gaussian splatting. So authored by Yue Hu, Long Liu, Meido Chen, Peter Birrell, and Andrew Fang. Will be presented by Yue.
So hello everyone, my name is Yue Hu. I'm from the University of Southern California. I'm very happy here to share our recent work, Splat Map, which is online dense molecular SLAM with 3D Gaussian splatting. So to begin with, we need to talk about why this real-time high fidelity 3D reconstruction matters here, because the real-time high fidelity 3D reconstruction is a foundation for a lot of like intelligent perception in robotics or AR, VR, or some other autonomous driving systems. So it could enable this device to like understand and react with this environment better. So this work we are focused on explore how this 3DGS and the SLAM could help to this goal. So before we go into our pipeline design, we should like take a quick look of how traditional visual SLAM is work. So traditional visual SLAM, it usually starts with the sensor data. Sometimes it's the RGB, sometimes RGBD, but as we know that RGB without depth is a little bit more challenging compared with the input RGB data set. So, and then in the front end, there will be a visual odometry to estimate the camera pose, and in the front end, they will they will get the feature extraction, and they will do the data association. And at the back end, they will optimize the camera pose and refine the camera trajectory. And when the system detects there's a visited place in the environment, they will do the loop closure to refine the whole system, refine the entire scene. So as the output of this SLAM system, there will be two parts. First is the camera tracking trajectory, and the second is the 3D mapping results of the environment. So to summarize this system, it typically just take the RGB image as the input, and at the same time, at the output end, will output the tracking and mapping results. So there's a challenging for the traditional visual SLAM that could limit the traditional visual SLAM in a lot of downstream applications, which requires for like high fidelity, sufficient fidelity environment applications. So that is because the mapping part, they are typically using the point cloud as the representation method. So this could be like more low complete. It could be like easier to faster to compute, but it would be like limited some of the other application like AR, VR in the real world. So that's why in the previous years, the people started to integrate the NERV into the SLAM systems mapping part. So because NERV could provide with high fidelity 3D models compared with point cloud, and also it could provide a continuous like scenes with very nice representation in the scene. But the problem is the NERV requires substantial computational resource, and also the rendering time spends like usually hours to days, and also it's more designed for the static things compared instead of the SLAM real-time applications. So that's why we take a look at the 3D Gaussian splittings. So 3D Gaussian splitting could provide like real-time operations, could support very high frame rate execution. So that's perfect suit for the SLAM systems. And also they could provide a high fidelity reconstruction results. And also it's more suitable for dynamic scene. Like it could adapt to changing scenes without need to like retrain the entire scenes here. So that's why we started to think about if we could bring the 3D Gaussian splitting into the traditional SLAM pipeline. So as the tracking part of the pipeline, we basically it's basically based on the traditional droid SLAM system. So similar to what other SLAM did, we take the input of the monocular video streams as an input, and we create and maintain a graph, frame graphs for each frames. Whenever there's a new incoming frames into the systems, we will add a new nodes to the frame graph and updating the age between the graphs. The age is representing the correlation volumes here. And then different from other like orb SLAM, from other more traditional SLAM method in this droid SLAM structures, we also implement the camera pose and the depth estimation method differently. So for the at the very beginning, we just estimated the depth and the camera pose based on the previous images, and then we based on this T and the D here to calculate the induced flow. And at the same time, when there is an incoming frame into the system, that we will utilize the pre-trained model raft to calculate the optical flow between these two continuous frames, and then this optical flow, this predictive flow and together with this induced flow will be feeding into the convolutional GRU, and then output from the GRU is the confidence of each point on these incoming images, and also the reversion flow of between these two images. So this reversion flow will help us to understand how we should modify and revise the previous estimated induced flow. So with this help, with the help from the reversion flow, and together with this induced flow, we will have the predictive flow, revise the predictive flow, and with the help from the dense bundle adjustment and also the confidence weight, we could update and refine the previous depths and the camera pose T. So this process will be done every iteration when there is an image coming to the system, and we'll do this for the keyframes, for all the keyframes for each iterations. So that's the tracking part. And after this, for the mapping part, what we did is we already obtained the depths from the tracking part, and we utilize the current frames camera pose to back project and get the initial 3D Gaussian points here, and then we introduce the 3D JS training method into the system, so we could utilize the estimated camera pose to project the current initial 3D Gaussian points, and then we feed this into the differentiable tile rasterizer, like what the 3D JS did, and compare this render images with the ground truth images, and utilize the RGB loss to minimize the RGB loss to help refine and optimize the 3D Gaussian scenes. So until now, this pipeline, this naive version pipeline has already finished the structure of combining 3D JS, bringing 3D JS into the mapping part of the SLAM. But the problem is, so far the constraint of the scene is only based on RGB, and there's a lot of method pretty similar to this, like nerve SLAM or early Gaussian SLAM method, which is just a stop at the pipeline right here. This will have a problem. Challenge here is that it lack of the geometry constraints in the whole system. So sometimes the view will be overfit. So sometimes the results will be overfitting to the trained view visually. So let me explain why this happened. Is because at the very beginning of the SLAM method, usually the estimation of the warm-up phases of the SLAM is not that accurate. So that means there will be, so even though the initial wall is like the right lines here, but there will be a lot of like floating Gaussians and also like noise around this wall. So these will look like a ghost walls in your scenes, especially when the camera started with a plain wall. So it's hard for the SLAM to estimate the correct depth right here. So this problem is difficult to fix from the SLAM side, but we could modify some of strategy to improve this performance. So you could say that this is a top view from this room, that you could see the yellow lines, dot lines here is the ghost walls that generated from if we just only use the naive pipelines designed here. And there's also a ghost chairs. There should be only 2 chairs right here, but there will be some ghost effects here. So this could like, even though the training view, some other previous works training views looks perfect from some angles, but if you look from the out of the main view, this ghost walls and ghost furnitures will become an issue in the real world application. So that's why this hinted us to design. So not only just to finish this pipeline, we need to design some other strategy to decide how to update, remove from, and pruning the current scene. So so first we to refine the Gaussian. So firstly we designed how to make a mask to decide which point is reliability, has reliability, or which point need to be modified. So so we basically design a strategy based on 3 different constraints. The first one is the depth consistency. So this will make sure that the point depth is great. It's relatively same across different views, and also it's valid only if the reproject depth is stable in the recent keyframes. And also for the other one is the geometry consistency. Is we introduce the 3D point representation error across frames, and we're trying to make that as small as possible, and we set the threshold to make sure the geometry won't go too far from each other when the 3D point supposed to be very close to each other. And the third one is the graph. Is a graph confidence weight. This is coming from the tracking parts convolutional GRU. We have the confidence of each point, and we also utilize this confidence weight to decide which point should be kept and which point should be updated and which point should be removed. So with this mask design, and our said well then following doing the 3 different decision, like if we want to adjust the current 3D GS points or with the new updated camera pose and the depth, or we need to like remove these points because it's previously the points is here, and in the new iteration the points is removed. Then the SLAM side, then the Gaussian side will also keep removing this redundant point. And also if there's a new point coming out from the SLAM tracking part, we'll generate the new points accordingly. So, and then this is the image that shows. This is the image shows that after we did the SLAM informed adaptive classification, you could say that the point is perfectly gathering and generating and densification near the walls that is a real wall, instead of just having a lot of ghost walls, something like this. So so that's why we introduced the SLAM-informed adaptive densifications here. And every time when there's a new frame coming into our systems, we will update all the depth, camera pose, and also we update our mask to, and then we feed this information into the SLAM adaptive densification, and we modify the current 3D Gaussian scenes. And besides this, we also, to further improve the geometry constraint, we also introduced a geometry-guided loss here, which is basically calculate normal based on the depths we estimated from the SLAM, and use that to make sure the system is supposed to take the RGB and also the geometry into the consideration and improve the final results for final quality. So this is the tracking results about our system. So this data set, all the experiments was taken on an A6000 server. And also this experiments was taken on the replica data set. So from this is each room's result, and this is the average of the performance. And we evaluated the trajectory ATE, which is average trajectory error, as our tracking results here. And this is the SOTA method from nerve SLAM, and also the early droid nerve SLAM and early Gaussian SLAMs method. You could see that for the most of the scenes, our strategy, our pipeline works better than previous SOTA pipelines. So the average tracking error is trying to describe if the tracking results of you estimated from your SLAM system is close to the ground truth camera track trajectory. If it's more lower, that means your error is lower. That means you are predicting more accurate results here. And for the mapping results, which is the 3D reconstruction of the scenes results. So this is the example of replica ground truth, and this is our render results. So by comparing this, you could see that at least for this replica data set, we performs almost it performs very close results compared with the ground truth. And this is the ground truth. This is a fly through of the ground truth of the replica room 0, and this is our rendered results. So from those fly through, you could see that is pretty close to them. And let me see, there's a zoom in mapping results for the replica data set. You could see that this first two method is the night SLAM and the E-SLAM, which is a it's a SOTA nerve SLAM method, and also the glory SLAM and the photo SLAM, which is a monocular SLAM systems. They are Gaussian SLAM systems, early Gaussian SLAM system which is SOTA, and this is our method. You could say for the SOTA method photo SLAM, it's already very good at the scene representation, but still we are slightly having more details compared with the photo SLAM here. And there's some more other comparison between our ground truth and the photo SLAMs and Georeal SLAMs. So you could say that we could have some more detailed in the reconstruct in the scene, and it's better than other SOTA methods here. And the previous results are all showing on the replica data set, which is the synthetic data set. So of course, people believe that the replica data set could easily to get more higher performance. But now we also tried our method on the TAM RGBD data set. We only use RGB as the input instead of using RGBD. So we compared with another SOTA monocular RGB input, the Gaussian SLAM method, photo SLAM, and this is ours. So you can see that for the geometry and the RGB rendered results, we are having some details more clear compared with photo slams here. For example, the labels on the can here, and also the keyboards, and also the books and the edge of the desk. So, and we showed some quantitative results of the TOM data set. Of the TOM data set, you could say that not only we beat those SOTA mono method, we also could perform better than this RGBD data set input. That means this method, this Gaussian SLAM method is taking RGBD as an input, and we only take RGB as an input, and we still performs the best PSNR, SSIM, and LPIPS compared with them for the most of the scene. And this is also, we block the sound of the small module of our system to see that if you block more of our modules, the performance will drop. Only use the full module of our splat map, the performance will become it will reach the best performance. And this is the visual results. You could see that from A to E, we are adding more and more of other components in the system. So the results is becoming, it's becoming more clear. So that's the introduction of our work. I'm happy to take any questions. Thank you.
Questions from audience?
Right. Okay. Thank you. Thank you for your work. I'm by no means an expert on SLAM, but I've read some of them. And perhaps I've skipped your explanation on it. I don't usually see that as a recurrent component for SLAM work. So, can you inform me on why do we see a GLU module in your model? Because usually it's not a common design for SLAM models, as far as I know, anyway.
So sorry, I missed some key points. So you were asking for traditional SLAM as what?
No, like so not traditional SLAM. Sorry. Other 3D Gaussian, 3D GS-based SLAM works, I usually don't see a recurrent component. So could you inform me on why do you specifically choose a GLU component? Probably I missed your explanation on that.
Okay, so let me repeat. Are you asking for the comparison between my
the architecture
system and the previous early Gaussian splatting?
The architecture. I'm specifically asking about the architecture. Perhaps, yeah. So usually, I usually, at least as far as I'm concerned, I usually don't see a recurrent component in other 3DGS-based SLAM work. So could you explain to me why? What is the purpose of the GLU?
Of what?
Of the recurrent component, right in the middle, right?
You mean these two?
There's this blue rectangle.
This one?
Yeah, this one. Yeah.
Oh, that's a very good question. You actually
Okay.
asked a very good question, because some people will ask me. Seems like that's a very good question. Seems like my
There's
method
hidden
is
state. There's yeah.
Let me.
Of course,
move to
yeah.
the traditional. See, this is a very typical traditional SLAM method, and people will get confused. Like, I'm mostly working on this mapping part, and why our tracking result is still beating other Gaussian SLAMs papers. Like, we are still have better tracking results. So that could be the same answer to your question. Like, this is because in our some of the other Gaussian SLAM systems, they are using the orb SLAM or some other traditional SLAM method to estimate the depth and the camera pose here. They're using some traditional photogrammetry method, like to calculate between each frame, the correlation between each frames, and they try to guess the pose. And the difference from other SLAM is we're using the dry SLAM as the backbone architecture, structure here. So we could use the convolutional GRU to learn how to modify, how to reverse this dose flow, and modify this your estimated steps and camera pose. So this part will make sure this to be more accurate, and if we make sure this to be more accurate, then for the following matching part, because matching accurate representation.
Okay. I kind of get. I think I kind of get it. Perhaps I can ask further. Yeah, please.
Sorry, others like the org slam. I see a lot of Gaussian slam or nerve slam people. They are trying to use org slam, and the org slam is different from our dry slam architecture is because they are not. Sorry. So this part has an RNN inside this, so it's pretty compared with org slam. It's a little bit heavier. So, but it could provide you with more accurate this.
Okay,
TNT
and then
here.
I want to ask a very naive question. Have you considered transformer as a component?
That's a good question. That could be my next step for my thesis proposal.
Okay, why not go directly? Okay, all right. Well, perhaps that I shouldn't ask too much. Perhaps you're working on it already.
Yeah.
All right. Okay. Thank you.
Yeah. That's actually a very good question. So this could remind me to introduce some drawback of the system. So compared with, even though the photo slam, like the PSNR, we compare them, we are better than them slightly, but they're sometimes some of the dry slams method, some of the Gaussian slam method, they have much faster speed and or less computational costs compared with us, because this part is relatively heavier. But the good thing is we can have the better PSNR and scene reconstruction. So for some special downstream applications, so that's kind of like a drawback. Trade-off between this. Thank you so much for your question. Please. Thank you so much.
It's obvious that your method has achieved a relatively good result, but I would like to know your method's time-consuming and the testing hardware.
Oh, okay. That's actually another good question. So since I already answered this gentleman's question, so I could show the my backup slides here. If I can. You can see that. So this is actually I actually test our STEM systems for FPS and also the GPU usage of our system. Obviously, it's not as like beat every SOTA methods here, but it's relatively acceptable for some of the applications here. So I hope these numbers could answer your questions. Yeah. So thank you.
Sorry, just a quick follow-up on that. Did I miss what hardware you used on that one?
What, sorry? What
was the hardware that you used in that case?
I was using the 8000 RTX 8000 card, GPU card.
Okay.
Yeah.
Thank you.
Thank you.
Other questions? All right, let's thank the presenter.
Thank you so much. Thank you.